So in this lecture, I want to talk about objects in free fall. So an object is in free fall whether you've thrown it up, whether you've thrown it down, or whether you've just dropped it. Once you've let go in all three of those situations, that object is in free fall, meaning the only force that's acting on it is gravity. And gravity is equal to 9.81 meters per second squared. Now this next part, you're just going to need to be aware of how your instructor does it. Physicists, we're renowned for changing coordinate systems to fit what we like, and so we will make down be positive if it happens to be easier. Gravity, like velocity, is a vector, meaning it has a direction, and usually we will indicate that direction with the sign of the number, positive or negative. We can also do it just by writing up or down. Okay, so I'm just going to let everything be positive because I'm only going to be throwing down or dropping. So all of my motion is going to be in the down direction. I'm just going to let that be positive. If you have an instructor that says down is always negative, up is always positive, okay, just be aware. Or if she has a case where a person throws the ball up, right, then if the initial velocity is going up but gravity is going down, those two will have to have opposite signs so that they can be working against one another. Okay, so objects in free fall. Free fall, once, right, it's just out there in the world falling toward the ground. So here's the situation. So we're going to start from a very tall cliff. And let's say a woman has two rocks. One she's just going to drop, and the other one she's going to throw towards the ground, so toward the ground, down, with an initial velocity of 15 meters per second. So what I want us to find then is the velocities of both rocks at the end of second 1, second 2, second 3, second 4. Okay, so we're going to call the dropped one. So the dropped one will be rock A. So I'm going to use subscripts just to keep everything, so I don't have to keep writing that. So we'll have our time. So at 1 second, we need to find that velocity. So the one that she drops, right, it starts off at 0 because she's just dropping it, right? Let's go and it falls. So its initial velocity is 0. After 1 second, right, so after 1 second, it will have a velocity of 9.81 meters per second. So gravity, right, this acceleration, is telling us how fast our velocity is changing. It's going to change 9.81 meters per second every second. So how fast would it be going at the end of the second second? Okay. Well, it's going to change by 9.81 each second. So at the end of the second second, it will be 2 of those. So 2 times 9.81. meters per second, and I'm going to use a calculator, right, or 9.81 plus 9.81, right, if that's how you're going to do it. So 9.81 times 2, so 19.62 meters per second. You really need to be careful about keeping your units on your answers in physics classes, right? It makes a big difference what you have. It also helps keep you grounded and right in what you have. So at the end of the third second, right, it will have increased another 9.81, right, meters per second by the time it gets to the end of that the end of that third second. So if you still have that number in your calculator, you could just add on plus another, right, 9.81, so 29.43 meters per second, and our last one at the end of that fourth second, 39.24 meters per second. Okay. So now we know the velocity at the end of the first second, second second, third second, fourth second for a ball that we've just dropped. Okay. Now let's go ahead and do that same kind of calculation for the ball that we give an initial velocity. So at the end of that first second, right, it's going to start with a 15 meters per second velocity, and then it's going to increase by 9.81, right? So that at the end of the first second, it will have the 15 it started with plus that 9.81. I'm just doing my calculator work off to the side here. So 24.81. At the end of the second, it's going to have, right, an additional 9.81. So I can just add another 9.81 to that value I had before. Right? So now we're up to 34.62. Okay. Do it again. So each second it's increasing its velocity by that constant amount. So even though, right, for the two, for the dropped versus the thrown ball, right, they have different velocities, the increase between each, right, subsequent pair for, right, the thrown versus the dropped, that stays constant, right? So that delta velocity per 1 second interval, right, is the same for both. All right, now, so I can feel you tensing up. It's like, but wait, the one that is thrown, the one that she throws, that's going to hit the ground first because, right, it has more, and you want to say force, but it's not force, right? It doesn't have more force. The force is constant with that 9.8. It will have more velocity. You're absolutely right. It's going to go faster. It's going to get to the ground faster. That is absolutely true. Okay, so let's go ahead and just verify that so that your intuition isn't going to right, make you crazy. Because you're right. Your intuition is exactly right. So let's determine the distance traveled by both rocks at the end of each of these time frames. Okay, so now here's the next part. Wrap your head around. We'll look at the dropped ball first. So we determined that at the end of the first second, it's going 9.81 meters per second. It's not going that 9.81 for that whole entire first second. It's only doing that at the end. Right? If you think about either driving a car or right, pushing something along the ice, it doesn't start, right? It has to like get up to speed, as right you say. So it starts at 0 and then it accelerates and then it gets to this 9.81 at the end. So the gravitation, that force is a constant force, right? Gravity is a force, an acceleration. It's constant, which means I can just average, right, the final velocity at the end of the second versus the initial velocity. So if I said v sub 0, what it starts with, I can average those two, and that will tell me the average velocity over that first second. And then I would use, right, distance equals average velocity times time to come up with the distance traveled. Okay. In fact, well, okay, let's just do that. Let's do it a couple of times, and then we're going to make a great big old assumption here. Okay, so at the end of the first second, for our dropped ball, the average velocity is going to be, right, the initial 0 plus the final at the end of that second divided by 2, just averaging those two numbers. So my calculator tells me 4.9, I'm just going to go to 4.9, right, meters per second. And then the time that it travels that average value of 9.8 meters per second is 1 second. So 4.9 meters per second times 1 second, we can see the seconds cancel, so it will travel 4.9 meters. Okay. What about the ball that got thrown? How fast is that, or how far is that going to travel in its first second? Well, in that case, its average velocity will be its initial velocity But what was its initial velocity? Right, 15. And then the final velocity at the end of that 1 second, 24.81. Right, divide by 2. Average just means, right, add up the numbers, divide by how many? So 15 plus 24.81 divided by 2. That's not right. Hold on. Order of operations. I'll show you what I did. Can you see what I did wrong? Is that showing up on there? I didn't use parentheses. Right, so be super careful. So either parentheses or do it in 2 steps. I'll show you how to do it in 2. So 15 plus 24.81, enter, divide by 2. So 19.9 is the average velocity that that thrown ball will have over the time of its first second, so that the displacement, the distance traveled, will be its average velocity, meters per second, times the second that it traveled. Cancel those units, so it will travel 19.9 meters. Right, so it goes much, much farther. Okay, but the force on them is still the same. Okay, so if we want to find out, right, using this whole average velocity idea, we can just do that from, right, 0 to 4. Let's go ahead and do that instead of doing it at the end of 2, 3, and 4. So at the end of 4, so after 4 seconds, how far has each traveled? So if you want to pause and see if you can come up with that, you want to know the average velocity, and then you'll multiply that by the time. So dropped. So its initial velocity is 0. Its final velocity is 39.24. And that is over 4 seconds. So that's going to give us okay, I meant divide by 2, right, because I'm averaging 2 numbers. And so that will give us, hold on, let's turn my calculator off. So 39.24 divided by 2. So 19.62 would be the average velocity, right, if I average the final and the initial. And then the distance traveled is that average velocity, sorry, that was meters per second. So 19.62 meters per second. And that is, right, it will hold that average velocity for the 4 seconds it's falling. So cancel out your seconds. So 19.62 times 4 is 78.48 meters. So 78.5 meters. Okay, so that's if she just drops it. Gravity is the only force, it's in free fall. So now if we do it for the other example, right, the one where it gets thrown, let's find that average velocity over those 4 seconds. Right, so the initial is 15, the final is 54.24, divide by 2, my calculator is working. Again, enter in between or use parentheses, be careful with that. So it has an average velocity, right, the thrown ball has an average velocity of 34.62 meters per second. And so the distance it will travel will be that average velocity times the time it's falling. So meters per second times 4 seconds. Cancel the seconds, so times 4. So that is 138.5 meters. So it does travel a whole lot farther and faster, but only under the same force.